Let's talk now about the simple gas laws. So we talked earlier about the properties of gases, so pressure, and we talked about how pressure is measured using a barometer or a manometer. Now, scientists, they wanted to figure out the sort of relationships between the different components affecting gas. So those gas laws that they came up with, the aim behind them is to determine the relationship involving pressure, volume, temperature, and the amount of gas present. So we have four components: the pressure that affects, it's a factor that affects gases, a volume, temperature, and amount of gas. These relationships, the relationship between those components, they were actually determined experimentally, of course, and they were determined experimentally not by one person. Instead, it was sort of a sequence of experiments that happened. They were done by different researchers, and what those teachers did, they did a sort of similar type of experiment where you have those four components. One variable is shown to be dependent on the other, while the other two are held constant. So you have those four variables. You hold two of those variables constant, and you prove that if you change one of the variables, it will affect the second one that you have. So let's say you might change temperature while keeping volume and pressure constant, then the amount of gas would change. Again, this is just hypothetical. Amount of gas is the same, it's constant, but usually pressure, volume, and temperature are the most important variable factors. So let's talk about the first law, and it's called Boyle's law. And Robert Boyle, what this scientist did is he kept the mass of gas constant. So when you're saying the mass of gas constant, this means you have a constant number of moles or number of molecules present in a certain container. And on top of that, he also kept the temperature constant. So we have two constant things: the mass, so the amount of the gas, and the temperature. So by doing this, he studied the relationship between the pressure and the volume. So at this point, he wanted to see if there's any sort of relationship between pressure and volume. So for a fixed amount of gas at a constant temperature, Boyle found that the gas volume is inversely proportional to gas pressure. So what does inversely proportional mean? This means when you double the pressure, let's say, the volume goes down by half. So when we say inversely proportional, this means if one goes up, sorry for my lousy handwriting, if let's say pressure goes up, the volume will come down. So it's sort of the opposite behavior. So if one goes up, other one goes down. And this kind of relationship was, he made it into like a sort of equation, or a sort of proportionality equation, represented by P dot V equals constant. So the variability between pressure and volume, with the fact that the temperature is constant and the mass of gas is constant, they will always give a constant number. So this number will not change. Now, also, Boyle's law can be represented by P1 V1 equals P2 V2. What do we mean by that? So let's say we have a gas at a certain volume and certain pressure. So let's say the volume was 10 centimeter cube. Now, let's say the pressure at 10 centimeter cube was 20 atmosphere. So let's say we have 20, and then we have the gas, the volume was 10 centimeter cube. Okay, so that gives us 200. Okay, now let's say we switch this gas, same amount of gas at the same temperature, we switch it to a bigger container. So now the volume of the container is 100 centimeter cube. So how this equation works, or how could you use it, is you put this P1 V1 and you put P2, which we don't know, and we know V2. So you put the numbers down. So 20, so you get 200 equals P2 times 100. So now P2 would equal to 2 atmosphere. So you see there's a sort of relationship between those two values, and it will probably most likely be a question on exam, but it's going to be probably straightforward. So moving on to the next law, and now this law is called Charles' law. So Charles and Gay-Lussac kept the mass of the gas constant and the pressure constant. So the two components that they kept constant were the mass and the pressure. So remember, Boyle kept the temperature constant. Now Charles kept the pressure constant. So they studied the relationship now between temperature and volume. So how does temperature relate to volume? The conclusion was that the volume of a fixed amount of gas at a constant pressure is directly proportional to Kelvin temperature. Now, we didn't discuss Kelvin. We're going to discuss it now. Kelvin is a sort of unit. So let's say we use Celsius, we use Fahrenheit. Kelvin is mostly used in chemistry. So in chemistry, we don't use Celsius as much. The most common unit to use for temperature is Kelvin. So the first thing they found is that of temperature and volume are directly proportional. So unlike the relationship between pressure and volume, which was inversely proportional, temperature and volume are directly proportional. So what do we mean by that? We mean that if one increases, the other increases as well, or if one decreases, the other decreases as well. Now, they didn't stop there. Further experiments showed that volume and temperature are linearly related. So they go up linearly in a linear fashion. So if let's say we have a graph, when you raise the volume, the temperature raises, same sort of relationship. So what they found out is that although they differ at every temperature, so although the volume differs at every temperature, the gas volumes always reach a value of 0 at the same temperature. So we have different types of gases, let's say. So we have, let's say, hydrogen, we have nitrogen, we have oxygen. So what happened was they started varying the temperature and the volume, and they saw that there's a linear relationship. So as, let's say, temperature increases, the volume increases. What they also noted, though, is although they differed, the volume values, they differed at every other temperature, there was something common between all different types of gases, is that the gas volumes, all of them, they reached a value of 0. So they reached a value of 0 at the exact same temperature. And guess what? When they examined this temperature, it turned out to be negative 273.15 Celsius. So, of course, this cannot be reached in a normal situation. You can never reach minus 273.15 Celsius. But of course, using graphing techniques and mathematics, they were able to pinpoint this exact location of minus 273.15 Celsius. So this temperature is now defined as absolute 0, and the Kelvin temperature scale is used. So this Kelvin scale is based on this negative 273.15 Celsius. So what does this mean? This means that when you have the temperature in Celsius, so let's say we have a temperature of 10 degrees Celsius. 10 degrees Celsius, in order to know how much it represents in Kelvin, we add 273.15 to it, and then we get Kelvin. We get the temperature in Kelvin. Now, it's this unit is really important because for for gas laws, we will use a constant that I will talk about later that is specifically focused on Kelvin and not Celsius. So it's a big mistake that students do in exams. Students in exams usually mix up the units, or even sometimes they forget to change the Celsius to Kelvin. And remember, all the units have to add up to a certain unit. So if you use Celsius and you don't use Kelvin, then the numbers are going to be fully different and you're going to lose marks. So you got to be careful to use the exact units. And in chemistry, you have to focus on using Kelvin and not Celsius. So this is what I meant when I said graphically it's linearly related. We have the volume over here, and we have the temperature, and we have gas sample A, B, and C. We can see that they differ. The volumes differ at different temperature, but they all sort of intersect at a certain point where the volume is equivalent to 0. And this temperature here over here is 273.15. So Charles' law we talked about earlier, and we said how it's there's a specific point of which all gases intersect when we're when we're changing the temperatures with respect to volume. Now, we talked about this temperature being negative 273.15 Celsius, which they now call Kelvin. So next thing we're going to talk about is Avogadro's law. Avogadro's law, what happened is Avogadro, from the experiments of other people, especially Gay-Lussac's experiment, Avogadro concluded that equal volumes of different gases at the same temperature and pressure contain equal number of molecules. So what he meant is that the presence of equal volumes of gases at the same temperature and pressure. So when pressure and temperature are constant and you have gases of equal volumes, then you will have the same amount of molecules for both gases. So let's say take two equal volumes of gases. They have equal number of molecules if the temperature and the pressure of those two gases are the same. So if they are present in the same conditions, then of course they will contain the same number of molecules. If you add them together, you have twice the volume and twice the number of molecules. So it's just, all you have to know is that when the temperature and pressure are constant and you have equal volumes of different gases, then you will have the same number of molecules for those gases. So Avogadro, what he came up with is sort of a proportionality between the volume and the number of molecules, or number of moles, as you can see here. So what he realized is the gas volume is proportional to number of molecules and subsequently to the number of moles. So V is directly proportional to N, number of moles, and it's written by V over N equals constant. So now that we talked about all the different laws, let's talk about combining those laws together. We talked about the different types of laws, such as Boyle's law, Charles' law, Avogadro's law, in regards to gases and their properties. So now let's look at the bigger picture. So let's look at how those laws can be combined in order to form an equation that we could use in order to relate between the different properties, such as temperature, pressure, volume, and etc. So let's, for example, start with Charles' law. Charles' law can be expressed as V over T equals constant. Now, if we combining Boyle's law and Charles' law, Boyle's law is P dot V is constant. So pressure multiplied by volume gives us a constant. And V over T, which is Charles' law, gives a constant. So P dot V over T gives a constant. So by combining Charles' law and Boyle's law, we find out that P dot V over T, so this is how it will be written like this. So P times V over T is constant. Or in other words, if you have two conditions, let's say, for a specific gas, that will be the first condition, P1 times V1 over T1 equals P2 times V2 over T2. And that would help you solve equations, let's say, where you have the pressure and initial condition and the volume and the temperature, but you need to find, let's say, the temperature and the second condition when you have pressure and volume given to you. So now there's, of course, combining gas laws, and there's the ideal gas law. So we talked about combining gas laws, and We're going to discuss later the general gas equation that you could use in solving questions regarding gas. Let's talk about the ideal gas law now. So in an ideal gas law, this is the law where you have different variations in temperature, pressure, number of moles, and volume of a specific gas. So how did scientists come up with the ideal gas law? Well, first they combined those different laws together. So we have the P dot V, Boyle's law, V over T, Charles' law, and V over N, Avogadro's law. And that led to a P dot V is equal to N over T. P dot V over N multiplied by T is a constant, gives you a constant number. So over here, P dot V over N dot T gives you a constant. Now, this is usually written as P dot V equals nRT, where R is a constant. This is the ideal gas law. P dot V, so P multiplied by V equals N multiplied by R multiplied by T. R is a constant that does not change, so it's a specific value that we use, and we're going to talk about the different values that we could use for R, depending on what units we use. So the ideal gas law can be written in terms of moles or molecules. Now, when we're talking about moles, we use P dot V equals nRT, where N is the number of moles and R is the gas constant. But when we have, let's say, let's say we have a question where we are told that there's 7 times 10 to the power 23 molecules. So we're not talking about moles now, we're talking about molecules. In this case, we use a different formula, which is P dot V equals N number of molecules times K times T. K is Boltzmann constant. And again, those constants K and R have a specific value we're going to talk about right now. So for R, there's two values that are usually used for R. The first one is 8.314 joules per Kelvin per mole. So in this case, we have 8.314 joules per Kelvin mole. There's also other units we could use, such as Pascal meter cubed per Kelvin mole or kilopascal liter per Kelvin mole. The other value for R that we could use is 0.0821 liter atom per Kelvin mole. So just look at the units and you know what R value is. While K, on the other hand, is 1.38 times 10 to the power minus 3 joules per Kelvin. Now, in reality, it's joules per Kelvin per molecule, but molecule is just a number, so we don't actually incorporate it in the actual units. Now, you might ask, when do we use 8.314 for R, or when do we use 0.821? Well, of course, if you notice the stuff other than the values of R, you see that there's different units involved. So how do you start? How do you know which R would you use? Well, first things first, you collect the information that is given to you in the question. Number two, you use the conversion factors to convert data into correct units. So let's say you might have the temperature in Celsius. Well, you cannot use Celsius in the ideal gas law. So you have to switch the Celsius to Kelvin. So that's the first step. You make sure that you convert all the units into the correct form. 3. Determine the variable that is to be determined. So identify the variable that needs to be determined. So let's say they're asking you to find temperature. We know now that temperature is the one we have to find out. We use the equation, of course, PV equals nRT, and carry the units throughout the calculation. So the units have to be, of course, accurate. Let's say if we're using joules, or using Pascal for pressure, then it wouldn't be right for us to use, if we're given pressure in atmospheres, let's say 5 atmosphere, you won't be able to use this R, because in this R the unit of pressure is pascals, it's not atmosphere. So most likely, if you have the pressure in atmosphere, you would use this R. And then, for example, you might have the pressure in atmosphere, but you might have the volume in meter cube. This way, you would have to change the meter cube into the liter, and you can continue using the R that you have over here. Now, ideal gas law isn't just used to determine pressure, volume, number of moles, and temperature. It can also be used to find two other values that are really important in chemistry. One is the molar mass. So just to recall, number of moles equals mass over molar mass, and each molecular element has a specific molar mass to it. So sometimes the professor might teach you a question, might ask you a question, say, what is the molar mass of carbon? Given that we have 42 grams of carbon, the volume is carbon dioxide, gas, we're talking about gas. Volume is this much, pressure is this much, and the temperature is this much. So they give you all the information you need. So what you do is P dot V equals M over molar mass multiplied by RT. So if you write it this way, this might confuse you a bit. So it would be M over molar mass, and this one would be times RT. So now in this case, of course, just by switching sides and switching the unknown to one side and the unknowns to the other side, you can get molar mass equals, so let's go through it step by step. We have P dot V equals mass, molar mass times RT. So P dot V equals over RT equals mass over molar mass. So we want to know the molar mass. So it would be molar mass is equal to M times RT over P dot V. And from there you just calculate and you get the answer. Another importance for ideal gas law is determining the gas density. So let's say they ask us to determine the gas density. Well, density of a gas is mass over volume. So just by using this equation, we can you could see here, this is the mass and this is the volume. So in a way, we could substitute the mass over volume by density, and it would come up to density equals pressure times molar mass over RT. So you can see here that the ideal gas law is used for many different purposes. Finding temperature, finding molar mass, finding mass, finding number of moles, volume, pressure. Now, there's the ideal gas law and there's the general gas equation. So when combining all those gas laws together, scientists came up with the general gas equation that says it's usually used when there's an initial condition and a final condition, and it's usually applied in cases where one or two of the gas properties are held constant. So this is how it's represented as P initial times V initial over N initial times T initial equals P final times V final over N final times T final. So here you have just a sort of map to guide you through which law you should use and how would you use it, and what situations you would use it. So let's say we have the gas law problem over here. When the amount of gas is given or asked for in moles or in mass unit, we use the ideal gas law. So PV equals nRT. So this is in the case when amount of gas is given or asked for in moles or in mass unit. So when the amount of gas is in moles or in mass unit is not mentioned. So when they don't mention the amount of gas in moles or in mass unit, then we use the combined gas law, which is the general gas equation. Now, For using PV equal nRT, which is the ideal gas law, that's just straightforward. You just plug in the values and you get it. But using combined gas law, we have to know which scenario we have. The first scenario would be when, let's say, V initial equals V final. When V initial equals V final, we use Gay-Lussac's law. And Gay-Lussac's law says P1 over T1, which is P initial over T initial, equals P final over T final. So again, when V is constant, we could easily use P initial over T initial equals P final over T final. Now, if you ask me, okay, but where's the n number of moles? Well, when they give you the situation where the number of moles doesn't change, of course, they just change. Number of moles don't change when you change the pressure and temperature. It's held constant. So it's not actually required here because they cancel off each other. Now, if pressure is constant, we use Charles' law, which is V1 over T1 equals V2 over T2. And finally, if we have the temperature being constant, we use Boyle's law, which is P1 times V1 equal P2 times V2. Let's talk now about a different type of law, and this is called Dalton's law. Now, what Dalton's law states is that in a gas mixture, each component fills the container and exerts the pressure it would if the other gases were not present. So it does not matter if the gases are all present at the same time or they're not. Each gas will exert the pressure it would if the other gases were not present or if they were present. So it does not matter the presence of other gases. It does not affect how much pressure a gas would exert. Alternatively, each component acts as if it were alone in the container. So they act independently of each other. So the pressure they exert on the container is independent of the presence of another gas or not. So what Dalton's law concludes is that total pressure of a mixture of gases is the sum of the partial pressures of the components of the mixtures. So if you add up the partial pressures of the different gases present, you add them up together, you will get the total pressure of a mixture of gases. So we have an example here. This is the pressure of hydrogen, for example, in a container, and it's equal to 2.4 atmosphere. And the number of moles of hydrogen present is 0.5 moles. Hydrogen, on the other hand, here in the same container, it has a pressure of 6.0 atmosphere, and there is 1.25 moles of helium. Now, pressure total would be, as you could see here, the addition of the two pressures. So 2.4 plus 6 gives you 8.4 atmosphere. And as for the number of moles, the total number of moles is the addition of those two. So you can see here that the pressure total is just simply the addition of both pressures together. The pressure does not change based on other factors. Just you add up the two pressures and you get the pressure total. And same goes for the moles. Now remember that all the other conditions must be the same. You cannot, of course, add up those values unless they are at the exact same conditions. So over here we could see that the conditions didn't change. The volume was exactly the same and the temperature was exactly the same in all scenarios. And this is really important. So to put Dalton's law in a sort of equation, for any component I, PIV equals NIRT. So you could see here that the V does not change, R and T did not change, and this is the pressure and the number of moles that are related in this case. The total pressure is given by the sum of partial pressures, P. No matter how many, if there's 10 gases, you just add each partial pressure of each gas, add them up, and you get the total pressure. Now there is a sort of new term we're going to use. It's called mole fraction. Mole fraction is a fraction of all molecules in the mixture contributed by that component. So let's say XA. A is a gas. XA would be NA over N total, and it would be equal to PA over P total and VA over V total. So the mole fraction, you can deduce it from number of moles, pressure, or volume. One more thing we're going to talk about in Dalton's law is the common use of Dalton's law when collecting gases over water. So scientists used to use this traditional method of collecting gas collecting a pure version of a gas by the help of water. So what happens is, as you can see here, they simply extend the tube over to a bottle, and this bottle contains water, and then the bubbles from the bubbles from the tube go into this bottle and create this whole area that simply contains the gas that we are studying or we want to isolate. Now, of course, there's certain limitations to such procedures. We should make sure that the gases do not actually react with water or are water insoluble. That's the main point, because if they are water soluble, then they're gonna react with the water and they're gonna just mix with the water. So that would not be good for us. Now, how do scientists actually measure the pressure of gas from this? Well, they measure it by using the P total and then the mole fraction of the pressures. So the good thing about pressure of water is that it's pretty much known. It varies with temperature, but it's pretty much known based on the temperature. So let's say you're doing this experiment at temperature 25 degrees Celsius. We would know then there's a specific value for the pressure of water at that temperature. So we know that when the water is settled and we have this leveling, we know that the pressure of the gas and the pressure of the water is equal to pressure barometric, or the atmospheric pressure. So since we already know the pressure of water and we know this value, then it's pretty simple. Just do straightforward calculations in order to get the P pressure of the sample.